Well, just two announcements today. Two announcements. First of all, the minister's notes. This is the talk by George Kerr. These will be available to you after the lecture. Thought you'd like to know that. Anybody missing who dropped out of the groups, would you please let us know? We're trying to tidy these up. We've still got one or two ends to tidy at the moment. Now today we're going to hear, I think, probably an optimistic lecture on the whole, but one which will cause you to think in relation to other lectures you've heard. It's on atomic energy and nuclear power. And we're very pleased to have with us today Dr. Bennett Lewis, who is now the Distinguished Professor of Physics at Queen's University. Sure. He wasn't always that. He was born, of course, in England. And he went to Cambridge, where he gathered most of his degrees. He was engaged in radar research during the war, and then came to Canada when he had a very distinguished career with atomic energy. He was initially a division director of atomic energy. He then became, from 1952 to 1963, Vice President, Research and Development, Atomic Energy of Canada Limited, and then in 1963 to 73, the Senior Vice President, Science, Atomic Energy of Canada Limited. And he's not retired, of course. He's still working towards nuclear agreement. He's just returned from India, in fact yesterday, and I suspect that his talk will be laced with some of India's problems in relation to nuclear power and in relation to nuclear control. So, Dr. Lewis, here is your audience.
Thank you. This is my fourth lecture in this series of courses, but only my third year. So I'm reduced to one lecture, and I've got a terrible amount to say to you in this one lecture, because the amount of misinformation that is going around in energy is increasing, I think one might say, exponentially. It just grows. The message that I have, which is the same as in previous years, is that the days of low-cost energy are not over. They lie in the future, but a little way ahead. It's not immediately. In the next 20 years, you're likely to be paying a lot more for energy. But that is rather a matter of mismanagement. Nothing that the world has done to us, but just what humans have done. As Dr. Clark mentioned, I've just come back from India, and actually I was at a Pugwash conference at Madras discussing nuclear disarmament, which of course is a very important aspect of the future. If we do not disarm and go to nuclear war, then nothing of what I am saying is relevant, because after a nuclear war, and I don't know how long people would keep it up, there's likely to be rather few of us, if any, left, and the planet in a pretty good mess. So this is something that has been realized ever since 1945. But one must make a very great distinction between that use of nuclear fission in weapons and the use of nuclear fission to provide cheap energy. Because it is only petroleum and coal that will be becoming more expensive. There will be substitutes. That is to say, we expect synthetic oil to take the place of petroleum. And if you ask me what it comes from water and any carboniferous mineral, even limestone, with a supply of energy, and that energy can be nuclear. There is abundance of nuclear energy potentially available. So I've been in India, and I come back saddened, as I have on previous visit, because there's so little comprehension of the real state of the world. We, in Madras, while I was there was a little note in the newspaper saying that the electricity supply would be further cut back. It's supplied by hydropower, and the irrigation program is cutting back the supply of water, so that even for rural electrification schemes involving water pumping and so on, energy would be available from 10 p.m. to 6 a.m. And then at 6 a.m. they would switch off half the country, that is to say the provinces around Madras. And from 12 noon to 6 p.m. they'd switch it to the other half, and from 6 p.m. to 10 p.m. there would be none at all. And I also visited there the nuclear station they're building at Kalpakam, which is to use two 200 megawatt CANDU type reactors. In our collaboration with India, which started back in 1954, we were engaged cooperatively in giving them the capability of building their own power stations. And everything went really swimmingly until 1971. In 1971, they indicated that in the upper Ganges area, they wanted to build two 600 megawatt CANDU reactors. And we said, you must remember, we are in difficulty. You have not signed fully acceptable safeguards agreements that you will not divert material to making nuclear explosions. And anyway, we said, you don't want two, you want four in that area. 4 600 megawatt reactors. Well, last year, they have started on that project on their own with two 200 megawatt reactors. That is all. Because they will not, and they persist in saying they will not bind themselves to any international agreement concerning nuclear explosions. They want to retain all their options. And unfortunately, there seem to be a large number of people who think automatically that nuclear weapons are desirable in some way for the prestige or might, power, whatever you like, of the country politically. There are many people who quarrel with this, and it was well discussed by the United Nations back in 1967. There's a report on it in 1968, which indicates that there really is nothing to be gained and everything to be lost by pursuing nuclear weapons. I was there in discussion about, as I said, nuclear disarmament, nuclear weapons. And to put the hopeful side, there is a hope that we may find it possible to approach this disarmament on an area basis. That is to say, forbid nuclear weapons in a certain area and make all the people in that area responsible for policing themselves to see that this agreement is kept. But that's still many, many years away. In the parlance, it's called NFZ, which means Nuclear Weapon Free Zone. But even that has become unpopular, and so we introduced another idea of a global approach to a nuclear weapon-free world, because that is really what we're after. Down at Kalpakam, near Madras, they're building another 200 megawatt CANDU reactors. And when I visited that, they were rolling the tubes into the calandria that was made in India. Some of the shipping boxes still bore the name Canadian Westinghouse, but that is back from old times. Let's say the boxes are used over and over again in shipping these long tubes. So it's a CANDU reactor which resulted from our cooperation. But again, as I mentioned, it's too small. They will need much more. That reactor is not likely to be finished and in operation for the next 2 years. In their whole program, they have one 200 megawatt CANDU reactor in operation in Rajasthan, and another one that may be in operation this coming year. But then there are these two at Kalpakam near Madras, and then two at Narora for the Upper Ganges, where it is completely inadequate. Now, this was an international gathering, and we were discussing the problems of nuclear energy, which again are set very much by human imagination. And the Russians, for example, said their program was going ahead. They have no problem of public acceptance. Well, you can understand why, and it's quite true. But why should we have a problem of public acceptance? I'm afraid it's because there is no restriction on what is published that it shall be true. And many people have put out extraordinary stories. And for example, if I use the word plutonium, you probably all think this is something absolutely terrible and ghastly, a radioactive material such as one's never had before, and it's high toxicity. Well, all that is misinformation. Those of us, like myself, who have handled radioactive materials, we don't do it with the bare hands. We have the appropriate shielding. I would say that I would far rather be handling plutonium than polonium. And polonium was one of the first radioactive, naturally occurring isotopes found in the world. And I believe that anybody who has ever handled polonium and plutonium, and remember, we at Chalk River had 25 kilograms of plutonium, quite enough to be concerned with the necessity to avoid criticality hazards, so on. So I think we know. We would say plutonium is wonderful. And to give you an illustration of this, I want to say that people are very worried about radioactive wastes, because that is to say, the people that are not actually having to handle them. The people who actually have to handle the radioactive wastes, their greatest problem is the people who think that there's a problem. They themselves can go along fairly well because, and I'll give you an illustration. Just before I was born, there was a controversy in scientific circles because a mineral had been found in Ceylon, as it was then, Sri Lanka now, which was radioactive, but it contained helium at a pressure corresponding to 100 atmospheres. That's to say, the density of the helium in the mineral was at 100 atmospheres. And people said, helium, this doesn't combine with anything. Have we discovered a chemical compound? Because this helium must have been there for hundreds of millions of years. And it's in there. Well, this was shipped in small lumps, in bags, to England, where they then started to examine it and found that, yes, the helium was coming out, but at a rate that corresponded, in fact, to the migration of atoms in solids at room temperature. And if they heated this up, they could heat it up to 1,000 degrees centigrade when it would explode. But up to 400 degrees centigrade, very little extra was coming out. And this, of course, is part of science, trying to understand the migration of ions, of atoms in solids. And now we have a pretty good understanding. And this, of course, is what we apply when we think of managing radioactive wastes. We put them in solids, keep them cool. And instead of looking for a salt mine or a vast geological formation, all you've got to do is look for keeping a small little pebble cool. That's all. Even if you keep it cool in water, it doesn't matter, because the material coming out into the water is coming out very slowly, and you have other means of reconcentrating it, capturing it, putting it back. Well, I'm going to, at Dr. Clark's request, cut down on the economics this time, but not altogether. So I'll start off with the few slides that really concern this. If I have the first slide, please. This slide was produced back in 1953 in a very remarkable book called Energy in the Future by Palmer Putnam. I've been chasing that book in the Douglas Library, and I'm assured it's back now. It wasn't. It's been away for some time. Now, he was writing in 1953 at a time when all this harnessed nuclear energy was secret. So he couldn't say very much about it, but he postulated a prudent trustee of world energy and said what can he count on at, of course, a reasonable cost up to the year 2050. And he introduced a rather large unit, the Q, which you'll see is used here. I won't have time to explain and discuss it, but it is a unit of energy. And he said, what energy does the world have from income sources? That is to say, solar heat collectors. And remember, his book, published in 1953, had a photograph of a solar heated house in Massachusetts that was there in the 1930s. Don't imagine that these things just happened yesterday or are just happening. He himself was responsible for the highest power windmill or wind turbine then made, which was 1.25 megawatts, which had operated on Grandpa's Knob in Vermont until March 1945, when there was a bit of a storm and one of the blades blew off. So I think the man who climbed up the tower and shut off the remaining blade that was rocking the whole tower deserves a medal. But anyway, that was finish to that project. Nobody thought it was worthwhile going on there. But Palmer Putnam puts, for this century, from 1950 to 2050, wind power rising to 200 million kilowatts. Remember, Ontario Hydro is about 20 million kilowatts. This is for the whole world by the year 2050. But the contribution from that would be 0.1 Q. Whereas, looking at the world population and giving a reasonable estimate of energy they might need. He said 72Q. But he said the plausible demand that this trustee would have to deal with would be somewhere in the range 72 to 487 Q. And of course it depends on the population and how much energy they have that is harnessed. And nowadays we would put a reasonable estimate as about 300 Q. But all this table is based on 72 Q. Where does he get his 72 Q from? He looks at the solar heating things, fuel wood, farm wastes, water power, that's all hydropower, solar power collectors, which again is a sort of biomass system of growing things by solar power and then combusting them or using them in some other way, geothermal energy, tides, etc., and added all that up, it came to 8.226 Q. So he says these estimates are very rough, let's call that 5 to 10 Q. What can we get now from the fossil sources? Coal, natural oil and gas, oil shale, and the tar sands. And he sets these things down, which came to 27.2 Q. So he said with this 27.2 and 5 to 10 there, we are short. And the minimum plausible requirement from nuclear energy, if it can meet the economic competition, would be 35 Q, which is larger than any of these. And incidentally, there's a very interesting thing, because he says that by 1975 we shall have grown to use so much oil that there will be a crisis, and we will be turning to hydrogenation of coal for synthesis, to synthesize the natural gas, synthetic substitute natural gas, or hydrocarbon, liquid hydrocarbon fuel. And this, of course, is what is happening, but what has happened since that he didn't know about was that the nuclear energy, harnessed nuclear energy, is so much lower in cost than the energy from coal that you wouldn't afford to burn the coal to provide the energy for producing this synthetic gas. But anyway, he's put here that there will be coal burnt to produce this synthetic gas. And even so, it's pretty small compared with the need. Well, it's worth thinking of this, because nowadays people are very apt to talk about alternatives in energy supply. There aren't any alternatives. You need all that you can manage if you're going to feed the world, Madras in particular. So let's have the next slide, which shows the evidence on which I made that statement that the nuclear energy is lower in cost than from coal. That's the electricity generated from nuclear power is lower in cost. These figures were given at an international conference in Paris in April this year, and they're updated to March 1975 dollar values. And from Pickering, this 2 million kilowatt nuclear station in Ontario Hydro, it's 7.03 mils per kilowatt hour. From the coal that's they had in their inventory, 13.26. But when they have to buy new coal, that's going to 16.18, which is more than twice the energy cost from nuclear. Now, when you consider that the real requirement for this energy is not here in Canada, it's throughout the world, and particularly where there are tens and hundreds of millions of people. And you cannot afford to provide energy except at the lowest cost. If you say, let us provide more energy from something at a higher cost, it means there will be less energy at the higher cost, because we can't organize ourselves. And this means not only ourselves in the developed countries, but the people in the developing countries to produce it. The next slide just shows what's been happening in Ontario Hydro from 1948 to 1974, and gives me the opportunity of saying that Ontario Hydro, by its organization, does not lose money. Its organization has just been changed, but for most of this period it was a cooperative of the municipalities. So the municipalities were both the owners and the customers of Ontario Hydro. They were presented with monthly bills, and then at the end of the year a 13th bill which would get them to pay for extra costs or give them a refund if what they'd been charged in the 12 months was too much. So although in any one year you can quarrel with the figures, and let me say it's not difficult to provide these figures, but the breakdown of the detailed costing in Ontario Hydro is a very complex matter. But this slide shows that although the price went up from 5.4 to 11 something mils per kilowatt hour in 1974, if we apply a medium price index that relates particularly to the gross national expenditure, shown here, then in constant dollars the supply went from 5.4 to 4.6 mils per kilowatt hour in 1972, 4.8, 4.7, still staying much the same. Now, Pickering's contribution to this is energy at 7.03, as we saw in, 6.22 in 1972, 7.03 in current dollars in 1975. But again, in constant dollars, that cost has fallen. I wrote a paper in 1970 addressed more or less to Ontario Hydro, and with their permission it was published, and you can still obtain it as $1 a copy from AECL, which gave the prospect of low-cost power in the future from Ontario Hydro. But they need to do something that they are not yet doing fully, even though they've got this successful Pickering with this low cost. That doesn't represent anything like the limit. And one of the major things is, of course, to slow up a little bit, not borrow money, but get out of debt. And getting out of debt means charging rather more, but you can still have exactly the same sort of formula that you will not lose money overall. And, well, they followed some of my suggestions, but not everything yet. They're still borrowing money at very high interest rate, which is part of what you call the cost of power in Ontario. It's really somebody who had some money lending it, getting a high interest rate. But it's not necessary. The next slide shows Pickering, this station, which generates 2 million kilowatts, 4 500 megawatt units roughly. And I'm just showing it because this is the turbine hall, which is 1,000 feet long. Now, I'm showing this picture because of the next slide please, where here is Pickering on the same scale. Now, if instead of being nuclear, it was to burn coal for 30 years, which is the life of the turbines, that is the volume of coal that it would burn on the same scale as that is the station. And this is the volume of the ash, and that's the volume of the fly ash. But it isn't a coal-burning plant. It is a nuclear plant. And that is the volume of the uranium fuel that it would take for 30 years. And that is the volume of the nuclear waste. Now, when you read the newspapers, you usually hear of nuclear waste as vast amounts of nuclear waste. Well, just get the perspective correct. That, in fact, is the volume of the nuclear waste relative to the size of the plant after 30 years. It is highly radioactive, or some of it is highly radioactive, and as I've mentioned, that doesn't worry the chemical engineers. They only get worried by people telling them that they've got an impossible job, because we put these wastes into glass at Chalk River in 1958, and we've followed them since, and it's all behaving perfectly according to knowledge, scientific knowledge, and there's no particular worry. When one looks to the future, certainly, one's thinking not of one nuclear plant, but some thousands or tens of thousands of nuclear plants around the world. There are some problems, particularly of arranging that people do not misbehave themselves. That is to say, supposing one worked up a war and somebody wanted to do somebody down, it has been suggested they might try using wastes or plutonium or something of this sort. But let's say those that have studied war games, the military analysts, don't think very much of that. But they may have an impact through an unreasoned fear. Let's say already around in the world there is this unreasoned fear about plutonium. And it's possible that by exploiting that unreasoned fear, people might make a threat that we are going to scatter plutonium over your city unless you do something of this sort. But that would be a rather unreasonable fear, because although we take the extreme precautions in handling plutonium, because we do not want to exceed 0.6 of a microgram in the human body, we're doing this by extrapolation as a precaution, but we still have not found any individual in the world, in all the nuclear projects that are known about. There are, of course, some barriers. In China we don't know very much, but what we do know suggests that there's no individual in the medical records who has died from the toxic effects of plutonium. So that's a remarkably good record when you're dealing with a highly toxic material, but it shows that it is also possible. So we've been there were, in fact, some tens of people back in 1945, when we were only dealing with the weapons program, and they were found to have, on the average, about 3 micrograms of plutonium in their bodies. Well, most of them are still alive, and none of them has died from the toxic effects of plutonium. Those that have died from other causes. So one must try and keep a reasonable perspective if we're thinking of guiding the world to energy. The next slide. This is to show that even coal is not going to last us very much. And this is a complete cycle from the year 1800. This shouldn't be years, it should be year 1800 to year 2800. And supposing we're able to get 7.6 times 10 to the 12th metric tons mined, which is an optimistic estimate, then it might stretch out in that way. If we take a pessimistic estimate and have only 4.3 times 10 to the 12th metric tons. Incidentally, 10 to the 12th metric tons is 1 square in this graph. Well, growth at 3.56% per year, which is a reasonable energy growth, supposing that coal was taking the whole of the energy growth, it would have to go up a little more steeply than shown here, which means, of course, it would come down sooner. The next slide indicates what this looks like on a scale of 5,000 years ago to 5,000 years in the future. This is the utilization of the total economically extractable and applicable coal in the world. So when we're talking about nuclear energy supplying all the world's needs for thousands of centuries, this is only 5,000 years, you see we're talking a completely different scale. And geothermal tides and all these other things we saw looked even negligible compared with coal. But we must keep the scale in mind. The next slide, I mentioned that we were going to get low cost. I mentioned 6.22 mils per kilowatt hour from Pickering in 1972, and that is the way that it was officially calculated. I say, no, we may be able to do better. We can have the station running for 90% of the year rather than 80%. We can have a little more automation in making the fuel, and we can tighten things up so that we lose a little less heavy water. And that would bring it down to something like 4.53. This is a sort of conservation kind of argument that you've been hearing from other people. That's if you make yourself more efficient, you could save your 30% or whatever it is. Then we've still got in our bag, but not doing anything about it yet, the reactor that I call Cinderella because of its superior graces and its present neglect, the CANDO with the organic coolant and thorium fuel. These reactors provide a higher power density, so that you can think of 4 1,500 megawatt reactors instead of 4 500 megawatt reactors as at Pickering, and these individual reactors would be smaller. One can get a net station efficiency of 39%, which means that the fraction of heat that's wasted is very much less. And the most important feature of Cinderella that is not shown here is that the coolant circuit in ordinary operation is not radioactive significantly. We've only got one small reactor working, but that's at Whiteshell in Manitoba. But I have often been in the main circulating pump room with the reactor at full power, which is only 40 megawatts, but the radiation level is quite tolerable. Now this is something which is completely different from water-cooled reactors. I, again, won't have time to explain, but anyway, not only will this have higher efficiency, lower radioactivity in operation, but the total cost in 1972 dollars would be about 3 mils per kilowatt hour compared with 6. And if we go back to 1949, constant dollars, 1.45 mils. Now the next slide shows the importance of this, because if you've got electric power at 2.5 mils per kilowatt hour, or 5 mils, then this is the cost that producing hydrogen would add to producing synthetic oil and gas. You'll have to refer to places where this is published to compare these numbers, but I'm sure you that these are right. And the figures are not astronomical. In fact, in cents per million BTU, we are way up over the 200 already in some major uses. So that this is the way that we will go when we follow what Palmer Putnam was saying, but use nuclear energy to liberate hydrogen, possibly just by simple electrolysis of water, and combining with carbon, which if it comes as carbon from coal, or if it comes from limestone, you see that the costs are up, but not astronomically. In other words, these thousands of centuries, we're not going to run into trouble with the Earth's surface. There's plenty of it. The next slide is developing the argument that I gave to Ontario Hydro about how they could reduce the cost of power following a nuclear route. We do not expect that we're going to go on expanding at 7% per annum indefinitely. Well, here, arbitrarily, it's said we'll take it on for 30 years, and after 30 years, we'll drop it to 4%. On the route that I'm suggesting, then you reduce the cost to about just over 3 mils per kilowatt hour. Or if you introduce the organic cooled reactor, you come down into this 2.5. Now, this is all in terms of 1972 dollar values. And it's a very low cost. So that, and let us say that we're not going into debt, therefore there is not much problem on the capital. But you see, in order to get out of debt, we have to pay something like 20 or 25% more for 10 or 15 years. And it's really worthwhile putting ourselves on that time scale. That would really be one of the most important ways to save money in the energy business. The next slide is the key to what I mentioned for storing radioactive wastes. And it's a sort of trick, but it's well known to chemical engineers and chemists as the Arrhenius plot, plotting the reciprocal of the temperature here against a diffusion rate or something of that sort. Well, a rather convenient thing is to take the time that an atom stays in a position in the lattice of a solid. And here we see this scale is like this, that hydrogen in alpha ion, its dwell time, even down to 127, and let's say we take it down here, is it between 1 nanosecond and 1 picosecond. 1 picosecond is 10 to the minus 12 of a second, 10 to the minus 9 of a second. A microsecond here, a millisecond here, 1 second, 1 year, 1 million years. And here we see that when the activation energy is in the region of 2 electron volts, an atom can stay, even at 100 degrees centigrade, for 1 million years before it changes its neighbor. And this is the key to storing radioactive waste. You do not think of large formations, you think of a little pebble, and think of storing it in that. Why a pebble? Because you've got to keep it cool. And you can keep it cool if it's got enough surface. The next slide takes us on to some of these other problems and horrors that run around, usually in the form of misinformation. This actual table was taken from an annual report of the Australian Atomic Energy Commission. The UK, the figures relate to the UK, and there's no reason to doubt them. This is the male staff of the UK AEA, the people that work. And if they were actuarially equal into the rest of the population, the whole population, it would have been expected that in these years, 62 to 69, there would have been very nearly 2,000 deaths. Well, there were 1,467. There would have been about 500 cancers. Well, there were 379. Lung cancers might have been 224, but there were 150. Leukemia might have been 13, and there were 6. Now, these are facts, but they do not make science. Science comes when you have consulted all facts over a wide range. But to suggest that these atomic energy workers, who are allowed to have 10 times the radiation that the population has, are seriously at risk, just doesn't seem to be true. We cannot say that it's going to go on in this way always. One can argue that they were selected by a medical examination and therefore they're better individuals than the average, and so on and so on. But let's just warn anybody who thinks that working with radiation, knowing what protection you must take and what levels you can go to, that it is then hazardous. There is always a risk, but it seems to be very well looked after there. The next slide also, hello, we've gone back. The next slide, no, I'm afraid that's not the next slide. We skipped one. That's the one. There has been an atomic bomb casualty commission studying the deaths in the survivors from the Hiroshima and Nagasaki bombs. And of course, they were primarily interested in those who were young, so that those who at the time of the bomb explosion were aged 0 to 19 years, they were collected together and analyzed, and the total number of such persons was 32,000. Now, they expected in a normal population 1,106 deaths in this period of 1950 to 1970, of 20 years. Actually, there was 1,147. And you can see from the next table that a good deal of the increase was in leukemia deaths. But again, the leukemia deaths are not very large in proportion to the population. They then broke it down to those that had received more than 100 rads at the bomb time. And there you see that, yes, the more than 100 rads has really put up the deaths from leukemia. But in the 0 to 9 rad case, there is no significant difference. In other words, even though there were 22,574 people, there was no significant increase. So again, don't think that bumper stickers that say leukemia penny cheap from such and such a utility really have any thing other than misinformation at the back of them. The next slide, will be the last one, is another thing that is still the subject of quite a lot of debate, because one of the questions, one of the low levels, one of the factors that sets the low level of radiation that can be allowed is the irradiation of a fetus, a human fetus, before birth. Now, it so happened that there have been 1,292 live births of those that were significantly exposed to the bombs, and there has only been one cancer death under 10 years. Whereas, if you take the pessimistic assumption on which we base permissible exposure, one would have expected 13 at that level, and in fact a total of 36.9, and there was only 1. And she was a girl whose mother had been exposed to 170 rads, so that clearly we're not dealing with low-level irradiations. And she didn't die of leukemia, it was liver cancer. But this is just to warn you against some of the misinformation. Thank you.
Thank you very much indeed.
I have some problems.